AP Biology students, we're going to go over the sixth and last page of the statistics assignment. And in this page, we're going to be looking at something called a chi-square. Basically, a chi-square analyzes if expected and observed values in an experiment match or don't match. Let's take a look at the question. You have a coin and wonder if it's weighted. A weighted coin will come up more heads or more tails than expected. You predict that if you flip a coin 50 times, based on a probability of 50-50, you will get 25 heads and 25 tails. Again, these are your expected or your predicted values. After you conduct your experiment, you observe that you get 21 heads and 29 tails. Now, what the chi-square is going to do is it's going to look at the 21 and 29 results and compare them to the 25 and 25. And again, this chi-square is going to take those results and compare them with the expected values and analyze if they are by random chance or if there is a variable influencing the results. This is the chi-square equation that we're going to use. Remember that x squared is chi-square. That big E or the summation sign is the adding up of all the values inside it. O represents observed data and E represents expected data. Now, before we begin, we have to make a null and alternative hypothesis. Remember, we can always have the null hypothesis as there's no significant difference between the expected and observed values. And the alternative usually is what we are hypothesizing or guessing what's going on. We're going to make the null hypothesis a little bit more about the experiment. It says there is no significant difference in the number of heads and tails flipped for the coin and the predicted values. Meaning there's no difference between a random coin flipping heads and tails and this coin that we're thinking might be weighted. The alternative hypothesis, the coin used in the experiment is weighted and will come up heads or tails more than the predicted amounts. This is what we think might be going on. Now, I like to show this chart to help us understand what the observed and expected values are for our experiment. We expect to get 25 tails and 25 heads. However, remember, in our experiment, we get 29 tails and 21 heads. So do these data, do the observed values match or at least are close enough to the expected values? If you look at the observed values of 21 and 29, yeah, they do kind of seem like they could happen by random chance. But we can't just say from an eye test that they are within random chance. We're going to use this chi-square chart to analyze if we reject or fail to reject our null hypothesis. I'll come back to this. We have to determine how many variables there are in this experiment, which degree of freedom we're going to use, and our critical value for this experiment. Remember that there are only two outcomes. There are only two variables, heads or tails. That means our number of variables is 2. To find the degrees of freedom over on this left-hand side, you take your number of variables and subtract 1. Since there are only two variables, heads and tails, we're going to subtract 1 from that and get 1. We're on the first degree of freedom. Again, here's our degrees of freedom. We're on this first line of the chart. Now, what I like to show students is if you see this 3.841 under the 0.05, you know we're in the right column. We again look at the strength of evidence of being a 95% confidence rating, which matches up to that 0.05. So there's a lot of other statistics that go behind this, but just understand we're only looking at this column here, the 0.05 column. Again, taking a look at some of these answers. Number of variables, 2. Heads and tails. Degrees of freedom is n minus 1, which is 2 minus 1, which is 1. Our critical value is 3.841. We again found that number right here, 3.841. We're in the first degree of freedom and we're under that 0.05 column. Now what we have to do is we have to calculate the chi-square. Here's our equation. Now we have to plug in the numbers. Remember, we have heads and we have tails and we're going to add them together. 21 is our observed for heads and 25 is our expected. 29 is our observed for tails and 25 is what we expect. Now again, we have 21 minus 25, which is -4, but I don't have it here. It should be -4 squared, which is still going to be the same as 4 squared because 29 minus 25 is 4 squared. So we bring it down here and they're both over 25. 4 squared plus 4 squared, 16 plus 16 is 32 over 25. 32 over 25 is 1.28. It's really important to remember, this is our chi-square. We don't have to square root both sides to get x by itself. X squared literally means chi-square. So that is our chi-square number. Now what we have to do is we have to take this 1.28 and find where does it fall on our chart here in the degrees of freedom, the first degree of freedom specifically. If you take a look, we have 0.455 and 2.7. So it's going to fall between these two numbers, which means our p-value up here, these are the p-values, is going to be higher than 0.05. We don't know what it technically is. We just know it's higher than 0.05. And if you remember, if our p-value is higher than 0.05, we fail to reject the null hypothesis. If our p-value would be on the right-hand side here, it would be smaller than 0.05, which means we would reject our null hypothesis. So again, our p-value is not 1.28. This is our chi-square value. Our chi-square value tells us that our p-value is larger than 0.05. So do we reject or fail to reject our null hypothesis? We fail to reject our null hypothesis. And remember, our null hypothesis is there's no significant difference in the number of heads and tails flipped for the coin and the predicted values. And that matches up with what we thought. Yeah, 21 and 29, yeah, they do seem like they could occur by random chance. And what that means is, yeah, we reject our null hypothesis because our p-value is higher than 0.05, and that means our data sort of matches what a expected value for this coin should be. And it kind of means that the coin probably isn't weighted. Now, we can't say for sure it's not weighted, but our data that we collected doesn't support that it is weighted.